Welcome everyone to this analog-based meeting track today. Today we're joined with Staats. He's a researcher working with the University of Arizona's Biosphere 2, and he will be speaking about high-fidelity Mars habitat simulation that provides unique educational experiences for citizen scientists. Kai, welcome.
Thank you. Thanks for having me, and thank you for joining. Look forward to presenting and then receiving your questions at the end. So as introduced, thank you. I'm Kai Staats. I'm a visiting researcher at the University of Arizona and Biosphere 2. And my talk, as similar to many of the talks, is about becoming interplanetary. And so I'll be talking to you about two different projects. One is called CMOC and one is called SAM. CMOC is a computational model, a computer software environment, and SAM is the real thing. It's a habitat that we're building at the Biosphere 2. So I'm looking forward to sharing both of those over the next 20 minutes. So we'll start with some beautiful artwork that was created by my good friend Brian Biersteig, who's worked with us for a number of years. You may recognize his artwork all the way back to the days of Mars One. He's been involved in a lot of really amazing visionary projects to kind of give us a sense of what it might be like to live on another celestial body. And this environment that we're looking at, I would call as third, maybe fourth generation habitat. We know that our very first habitats are not going to look like this. We're going to start with something simple with basic capsule, but we want to get to this point, and even something more substantial has been presented in some of the other presentations today and yesterday. And to do that, we have to really understand the complexity of the things that we bring with us, especially if we're bringing plants and animals and complex biomes and ecosystems, not just mechanical systems. So the real fundamental question is, how do we sustain human life in these hostile off-world environments? And that's not easily answered. There's no one solution to that. And although we have a lot of technology, a lot of understanding, we don't have all the answers yet. There's still a number of things we have to develop in order to make that possible. At the core of that, of course, is our life support system, our environmental control and life support system. And I have two images on screen here. You'll see gears in the upper left-hand corner and a plant leaf in the bottom right-hand corner. And that represents the physical, chemical, or the mechanical life support systems that are being used today on the space station, for instance, and bioregenerative life support systems. We've heard a lot about that with some of the other presentations today, in particular the interstellar works. So we see perhaps in the future a combination or a hybrid approach with both of these. So on the mechanical side of things, this is a ground-based duplication of what's similar to what's running on the International Space Station. This is the machines that process that recycle the air and the urine and the human waste and make certain that the astronauts on the space station are able to live and breathe and have clean air and clean water for the duration of their mission. And something like this or similar has been running for many, many years on the space station. And this, of course, is the world's most famous bioregenerative experiment. And this is the Biosphere 2, just north of the Catalina Mountains in Arizona, outside of Oracle, about a 45-minute drive from Tucson. And this was constructed in the late 80s and ran through the mid-90s. There were 8 people who lived inside for 2 years. And there was an incredible amount of knowledge gained, both through things that worked and things that didn't work, that are still today teaching us about what it will be like to try to build a bioregenerative system on another celestial body. An incredible experiment. If you haven't visited, please visit. In fact, they're opening up again just next week with some safe measures in place for COVID. So we're excited to have this open again. This is a newer, more modern version of that bioregenerative experiment. This is Lunar Palace, which ran for a few years, I think 2014, 2017, if I remember correctly, maybe 1 year after that. This is a different approach. This is not this large scale, multiple biomes and 3.5 acre seal. This is relatively small vessel that has a lot of hydroponics and, as you can see, high density growing arenas. This is probably more close to, in fact, we believe this is closer to what we will be taking with us or building on the moon or on Mars, because it takes up less space, it takes up less resources, and it can be computer controlled, et cetera. Fantastic experiment. If you haven't read about Lunar Palace, please do. Lunar Palace create a system flow, which I love. This is a very simple system flow. It shows plants and the atmosphere and crew and the urine and waste treatment and recycled water treatment and condensates. Everything is in here. I won't go through all the details, but this is a really nice way of visualizing the complexity and how all this system works, how everything moves together and is recycled and comes back into the environment again and again and again, which is a really important understanding for any time you see a human, what's called a human in the loop closed ecosystem. So that takes me to CMOC. And CMOC is as I said at the beginning, it's a computational engine. It's a research grade computational engine with a beautiful web interface, an educational web interface wrapped around it. This was funded by the Arizona State University School of Earth and Space Exploration Interplanetary Initiative from 2017 to 2019. And I was fortunate to be given a capstone team, an undergraduate capstone team, 5 really cool guys who worked with me for a year to get the prototype going. And that was their graduate project, which was fun. And then we took it into gradually transition from some of those guys who stayed on staff for another year into professional developers. And we're still maintaining and running that today at National Geographic. I'll share a bit. So CMOC is different than maybe what you might do with a spreadsheet or you might do with your typical discrete formula. This is using an agent-based model, which means we define agents as semi-autonomous entities within the software itself. So a square meter of strawberries or a square meter of wheat is an agent. A human is an agent. A solar panel is an agent. The habitat structure itself is an agent. And these agents exchange currencies. They exchange oxygen, carbon dioxide, methane, water vapor. And each hour of the simulated environment, they're exchanging these currencies. So to develop a conceptual diagram for that, I built this diagram in 2017. And over here on the left-hand side is what I started with. This is by Dr. Raymond Wheeler, who is a world-renowned researcher and physiologist, plant physiologist at the NASA Kennedy Research Center at the Swamp Works, wonderful name. And so I started with that and expanded it to this. And you can see there's a lot of agents. There's hundreds of agents, and they're all interacting, exchanging these currencies. And this is what we used to build. This was the foundation for CMOC. It was a lot of fun to really think through this and try to come up with a way of visualizing and then programming all the ways in which these agents interact. So this is just a real quick, I don't want to go too deep in the details, but for those of you that enjoy numbers, this is one example. This is the definition of the human inhabitant agent. And it defines the atmospheric oxygen, the potable water, the edible food, carbon dioxide, all the things that we breathe in and give out are defined within this model. And all these numbers come from, this one, the human inhabitant comes from the NASA's Human Integration and Design Handbook. And there's, all this is freely available resources that they keep updating every couple of years. So really amazing resource if you have, it's called BVAD, the Baseline Values and Assumptions document. Fantastic resource if you haven't seen that. So where it gets fun is when we're looking at the fruits and vegetables that we want to bring with us as well. So these images, by the way, are courtesy of Safeway. And so we want to bring with us a whole bunch of variety. So again, back to Dr. Wheeler at NASA, we started with his research, which is a compilation of all these different vegetables. So we have rice and wheat and cabbage and chard and celery. I know it's a little hard to read, but this is also freely available on our website. So in this data set is the amount of light that you need over a certain number of hours per day for a certain number of days from seed to harvest, the average grams per hour, the total biomass available at the end when you harvest it, and what percentage of that is edible versus inedible. Then we track nitrogen, phosphorus, potassium, water, atmospheric oxygen, atmospheric carbon dioxide. And what's fun to look at, this is my favorite part, is take a look at cabbage, strawberry, and wheat as an example. What do you notice? You notice that cabbage, we can eat almost the whole thing, 515 grams to 572 grams, it's almost entirely edible. Whereas strawberries, only about 1/3 is edible of the total biomass of the plant versus wheat, which is a little bit less than half. But where it gets really interesting is when you look at the amount of oxygen produced, the amount of CO2 sequestered by each one of these plants. Clearly, strawberries taste good and we love them on our ice cream, but they don't do so well with the CO2 sequestration. Whereas wheat, however, does really well. Wheat is fantastic at pulling down carbon dioxide and producing oxygen. Now on the next set, we have sweet potatoes, tomatoes, and green onions. Again, green onions, you can eat the whole thing. You could really eat all of it if you don't mind getting a little dirt in your teeth. Tomatoes, not so much, about a third again. And or about, yeah, a little bit less than a half. And sweet potatoes, however, look, again, fantastic at CO2 sequestration. So if you compare wheat and sweet potatoes, almost identical. The difference is that wheat takes forever to grow, and we can't eat it directly. We don't have multiple stomachs to digest a hard grain. We have to process it. So at the biosphere too, these two plants were both planted, and they learned that it took 7 months to make their first pizza, to plant the wheat, to grow the wheat, to harvest the wheat, to process it, and then to turn it into pizza dough. Took forever. But a sweet potato you can eat straight out of the ground. If you cook it, it's even better. They ended up planting sweet potatoes all over the biosphere and all the biomes, and they ate so many sweet potatoes that their skin turned orange after not too long of eating. And also the sweet potatoes satisfied that craving for something sweet. Nutritionally, the biospherians were fantastic, but from a needs standpoint, they wanted more sugar. If I remember right, they had to lock the bananas behind a locked door so people would sneak in at night and eat all the bananas. So these are the things that we have to really think about as we go to another planet. What are we going to bring with us? Okay, so this is the CMOC demo. And I want to start with National Geographic. Many thanks to National Geographic. I've worked with Educational Director Tyson Brown, who's been just awesome to work with the last year and a half. So National Geographic is hosting CMOC for the world to use for free on a Google Cloud platform. And it's just been outstanding to get their feedback and their support and their guidance. And the link to this is on our CMOC website. So I'm going to go through this very quickly. I usually spend over an hour just on CMOC demonstrations alone. There are videos on the website that take you into more depth. So we're going to go to, I've already logged in, we're going to go to a new configuration, and I'm going to choose a preset, the one human preset. The reason is it just gives us a baseline to work with, and we know what the outcome will be. So our location is on Mars. It's a 10-day mission duration. We have a small crew quarters from a choice of 3. We have 1 inhabitant, 100 kilograms of food, which is plenty, life support, one Eclipse module, and no greenhouse, no plant species, solar array, and batteries. Over here, we have a wiki, a built-in wiki that teaches us about each one of the items over here, or you can click on the eye there. So if you want to learn a little bit more about the selection, you can just click on the wiki icons, and it brings up that. The graphs show us a rough estimate of how we're doing on choosing, for instance, our solar panels. Do we have enough solar panels? Yes. This is our power production. This is our power consumption. So we're going to go ahead and launch the simulation. This is where you hope that it actually works. Okay, it worked, good. So our simulation is now complete. You can see that it's very fast. And so we've simulated 10 days. I'm going to go through this fairly quickly. So this is our power production by the solar panels, which of course is a bell curve with the rising and setting sun. This is power consumption by some of the equipment that we have on board. And this is the CO2 being sequestered or being drawn down by the mechanical life support system. So you can see this spike here is the power draw required for that machine to run. And if you watch the CO2 over here, when we reach that 0.1%, we want to draw it down again. It goes up, it goes down, it goes up, it goes down. So for 10 days, pretty much the same thing. It's a person, it's a machine, it's a closed environment. You really don't see any behavior outside of relatively linear behavior. And on the right-hand side here, we're tracking a lot. We're tracking atmospheric components. We're tracking the battery, the food, the urine, the waste, etc. And down here, of course, are multiple diagrams. So I'm going to log out of this one. Actually, yeah, I'm going to go back to a new one here. So we're going to do a new simulation. Now, this time I've preloaded it just so that things go a little bit faster. So this is now a one human with 40 square meters of radishes. So watch the difference. This is where it gets really interesting. Initially, it looks the same, except what is this? This is the plants turning, or the lights turning on and off, the LED lights turning on and off, consuming power to grow the radishes, because we know there isn't enough ambient light on Mars without using mirrors and reflectors to actually grow much of anything. So CO2 initially, the CO2 sequestration agent within the Eclipse rack is doing its function. But watch what happens over time. Over time, look at the bottom of that. It goes up, and the amount of time that the machine has to turn on is reduced. Less and less and less until it's just barely on for a moment, and then it's gone. Why? What happened? Well, look at this. The radish is now 85% grown. 40 square meters of radishes, 85% grown. The radishes are now conducting the life support. They're now drawing in the CO2 and putting off the oxygen such that our mechanical system is no longer required. We just transitioned from physical, chemical to plant-based bioregeneration for the recycling of the air. Now, we're not dealing with the recycling of the water at this point, or urine or waste products. And it is included, but our mechanical life support system is still doing that for us at this time. So we continue now with an entirely bioregenerative until we harvest the radishes. The radishes are harvested, boom, what happens? CO2 sequestration drops because the radishes are yanked out of the ground. And now our mechanical life support system has to kick back in again. That is the fundamental beauty of this environment that we've created. And this is really just the beginning. I'm just showing you one human, one radish. Now let's go to a much more complex environment where we have onions and red beets and radishes and cabbage and wheat and some free space. We still have lots of free space. This gets far more complex if I scroll through this. You get some erratic behavior because we don't actually have enough CO2. Some of the plants don't grow to their full potential. It gets a little crazy. So to think that we just throw a bunch of plants in a room and boom, we've got bioregeneration, it's not that simple. We need to now draw in CO2 from the outside to make certain that the plants have enough to breathe, because there's only 4 humans, and that's not enough to supply carbon dioxide for all the plants that are in this environment. You can see our CO2 is at 0. It's absolutely gone, and that's why the plants are starving. They're not doing well. So there's a lot to learn from running these models and running these simulations. Okay, so I'm going to, let's see, do I need that over here more? No. So I'm going to switch back over to, let me log out of this. Just want to reduce my poor computer, which is overheating. Okay, so the demo went well. I don't have to use my backup slides. And I appreciate your patience. I know I'm going through this very quickly, but again, all this is available for free. We do offer a 65-page curriculum for, it's a next generation science standards aligned, next generation science standards aligned curriculum designed for virtual and physical classrooms. So if you are an instructor, or if you are a classroom or virtual classroom instructor, we encourage you to download the guide. It really helps you create an entire curriculum around CMOC for anywhere from an afternoon all the way up to a couple of weeks within your classroom, grades 5 through 9, or 5 through 8, and 9 through 14. Okay, so now we're getting to the really fun, well, it's all fun, but this is the even more fun part. This is about SAM that we're building at the Biosphere 2. So we're gonna take a step back and just think about analogs for a moment. Analogs have been used for a long time, since the 1960s. Gene Shoemaker, who I had the privilege of meeting on several occasions when I was younger. Gene Shoemaker helped orchestrate and really facilitate some of the initial Apollo astronaut training in northern Arizona around Meteor Crater. We've got NASA's NEMO, NASA's Hera, we've got High Seas, MDRS, the Lunar Palace, and many, many more. I couldn't fit them all on one screen. These analogs are not, it's not a place to pretend. We're not pretending we're on Mars, right? We're actually practicing and training. There's psychological training, there's food study training, there's everything from donning suits and doffing suits, the challenges of working in confined space with confined resources, taking a shower with less than a gallon of water every 4 days or even less. Those are things that we have to learn how to do well if we're going to actually live in these confined environments in that first generation, second generation, even third generation habitats on the Moon and Mars. So these are valuable, and I was fortunate to be a part of the Mars Desert Research Station crew number 134, had an incredible experience, hard at times, but life-giving experience that really has influenced why I'm doing this today. So both of these research projects have come out of my experience at MDRS. So thank you to the Mars Society and to Robert and Shannon for making that possible. We're gonna go back to the biosphere now. So we're back at the biosphere in Southern Arizona. And we're going to focus on the test module. This is a very unique building designed and built by Tabor McCallum, who gave a presentation last night, and he gave a shout out to us. Thank you, Tabor. This was the very first experiment at the biosphere while they were building the real thing. They built this small vessel. It's about 24 feet by 24 feet by 20 foot tall, about 11,000 cubic feet. And inside of this, 3 women lived consecutively for a total of a month in complete isolation from the outside world, to prove that you could do it in a relatively small space. So we're taking that test module that's still standing today, still waterproof, needs a little bit fixing up. There's a lot of plants and some rattlesnakes and a few pack rats, but once we get those cleaned out, we're going to have what we believe to be the world's highest fidelity Mars analog. This is a completely hermetically sealed environment, complete with crew quarters, dual airlocks, differential pressures between, or different pressures in the greenhouse versus the crew quarters, different CO2 levels, different humidity levels. And this, like MDRS and high seas and other analogs, is a place where you can visit. We're excited about receiving your research proposals and for having teams coming for up to 2 weeks at a time within this environment. As the previous slide showed, we're going to be building, not immediately, but building a half-acre Mars yard, one of the largest Mars yards in the world, complete with a lava tube and a boulder field for rover tests, for EVA tests, for pressure suit tests. And we're very fortunate to have right in our backyard the University of Arizona and CMOC. CMOC is an advanced research agricultural center. For 30 or 40 years, they've been doing some incredible work in plant physiology and preparing for Mars, closed environments, sealed environments. So Dr. Murat Kassira and Jean Giacomelli and all their student body have been working with us for the last year and a half to both fine-tune and inform CMOC and now design SAM. So the University of Arizona and CMOC will be directly involved in this from day one, and we're really excited to have that level of expertise on board. We also have the good fortune of working with Pacific Spaceflight, who is providing all of, Dr. Cameron Smith and his crew are providing all of our initial pressure suits. And we hope to expand that, of course, to have other pressure suits in different entities as well in the future. So principal 5 objectives, this is towards the end of my presentation. We have 5 science objectives. These are not limiting, these are just foundational. We're going to be, as I described, transitioning from physiochemical, which is machine-based, to bioregenerative, plant-based life support systems. Why is that important? Because when we go to Mars, we know that we can't take full-grown plants with us. They won't do well from a gravity to a microgravity back to a gravity environment. Everything we said and we know about them says that's going to fail. So we have to take seeds, which means we're going to arrive with nothing but regolith, which has perchlorates and mostly just rock. There's no soil to speak of. So we need to learn how to transform regolith into soil. And how do we do it quickly? We don't have years, we have weeks or months. How do we chemically and biologically transform this harsh, broken rock with nasty chemicals in it to make it fertile soil? That's not easy. We don't know exactly how to do that yet. There's a lot of experiments, a lot of work going on, but it's not a simple process. Science fiction makes it look a little too easy sometimes. We're going to study the microbiome of the built environment. We know that those microbes on the space station have mucked up electronics, and behind some of the stuff that's on the space station, there's these mats of biofilms and nasty green things that are sticking to everything. We don't want that. We want to learn, how do we manage that? How do we monitor it from zero? So we have a unique, from ground zero. So we have a unique environment that we're building a building that will be clean and start. What I'm saying is we'll have a foundation, we'll have a place to start for that microbiome. From first order and first principles. That's the exciting part from a research standpoint, and that hasn't been done before. And as I mentioned, pressurized suits and advanced computer models. Our ultimate goal with CMOC is to continue to inform CMOC as we gather data from the advanced data collection systems we're going to have in SAM, and then ultimately apply an AI engine to CMOC and turn around and let CMOC run SAM. That's the ultimate goal, is that we teach it, we train it, and then we say, hey, CMOC, it's your turn. You take over and tell us how to run or directly run SAM. And that's life support systems, plant watering systems, et cetera. So in closing, a bit of it's a mission statement, but kind of a summary that I really enjoy. We want to engage research teams from around the world in a hands-on scientific discovery to inspire the next generation to be engaged custodians of this planet while we explore new worlds. And I want to say thanks to the incredible team that I have supporting this effort. We have Dr. Joaquin Ruiz, who's the Executive Director of the Biosphere. We have John Adams, who's the Deputy Director. We have Grant Anderson of Paragon, which is an incredible organization. Sherry Boonstra, Don Boonstra, Brian Vierstig, Murat Kassira, and Jean Giacomelli, Cherry Murray, Kevin Bonine, and Ezio Melody, and Yuri Malavinov, who are both working on CMOC. And I just can't ask for a better team. You guys have been fantastic in working with us for the last couple of years. And these are our official partners. There's more. These are the official partners. I have to be careful. NASA is not funding us, so I put the logo on there simply because there's so many people at NASA that are supporting this and working behind the scenes to help us make this happen. So thank you to everyone for that. There you go. That's the end of my talk. Thank you.
Awesome. Thank you so much, Kai, for joining us. We're going to go ahead and start with the Q&A portion.
Okay.
We have one question. What are developing automated algae production units and want to do a proper mass balance analysis for a closed system for a long time? Would it be possible for us to add various algae types to CMOC and see how they perform?
Absolutely. In fact, I would take it to the next step is that let's bring algae vats into, if we can do it on a small scale, algae vats, bring them into SAM and then monitor them in the real world. Unless you already have an environment to do this, let's bring those algae vats into SAM, monitor them, digitize them, and take that data and then use that to inform CMOC. Now, if the data set's already out there, if you already have a data set for us, give it to us. That'd be great. We'd love to introduce that to CMOC.
Another question we have, is there a general upper limit for CMOC, or could it reasonably give values for a habitat of 10,000 people?
It can. There's no upper limit. One of the beautiful things about Python is that it's scalable, 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 and we're running it on the Google Cloud platform. It'll take a while if you have 10,000 people, and there may be some scaling factors that we employ. So for instance, right now, if we have 10 crew members, we treat them as one entity without variation amongst those crew members. But in the future, we want to turn on what's called our entropy engine, where each crew member is slightly different than the others. So it really depends on how you want to play this out. If you just simply want to look at the average values, we can run it as we do. If we want to actually create a little bit of chaos, we can actually introduce a stochastic factor where each one of those 10,000 human entities or agents is slightly different than the others. And then we get some really cool nonlinear functions within that space. But it's absolutely doable. There's nothing that would preclude us other than computational time and somebody who wants to pay for it.
And we have another question. What are the requirements to go for this mission and conduct research in this analog environment?
Good question. Because we're beginning construction in just 2 or 3 weeks' time, we have not laid down the full parameters for that. So I encourage you to go to samb2.space. It's a very simple form right now, just first name, last name, email address, and that you're interested. And by the end of the year, we'll have, if not sooner, we'll have a really good definition of what those parameters are. It'll be similar to other analogs where we request, how much water do you need, how much power do you need, what are your science objectives, what's your crew that you need to bring, and how long do you need to be there. And as long as the experiment is safe, and as long as it produces something that's novel, we don't want to reproduce someone else's experiment. It needs to be a relatively new experiment or an experiment that revalidates a prior one with slightly different parameters. Then we're very eager to receive those experiments. And those will be reviewed by a professional research panel.
And with that, would you say that you've ever had the possibility to compare CMOC data with ones of an equivalent real system?
I mean, have I had the opportunity or will we have the opportunity?
If you ever have, or if you will have the opportunity.
Right. So CMOC is built on existing data from real systems. And we're able to, I've done cross-validation where I take the output of CMOC, which is in a JSON file, I load it into a spreadsheet, and then I do a separate numerical analysis of the output and compare it to the input to make certain that nothing is lost in the system. We're now building into CMOC an additional layer of computational engine that will do that self-evaluation to make certain that the inputs and the outputs match and we're not missing or losing something in the middle. To then take that data and compare it to a real world system again, we haven't done it at that level. That's really what SAM is for, is we want to take the input variables, predict what we think will happen in SAM, measure the real functions within SAM, and then compare it to what CMOC simulated. Of course, it's going to be off. It's not going to be perfect. And then find out why. Why was CMOC off? Was it off by 10%, 20%? Was it completely off? And how do we then modify the variables and the functions of CMOC to more closely match the real world? So SAM will be our first effort in that respect.
Awesome. I just want to thank you again for joining us. This has been a really great lecture, and we're really glad to have you this year. And thank you everyone for joining us on this lecture today.
Thank you, everyone. Thanks, and hope to see you at CMOC. And Sam, do send an email soon.